In this video, we are going to begin our last prerequisite that we need in order to start properly analyzing code. That's going to be summations. It's going to turn out that pretty much all of our analysis of code is going to hinge upon the fact that we know how to analyze summations. So, we're going to try to introduce a notation that is convenient and concise and can be worked with easily so that we can actually analyze code in an efficient way. So the first step of that is we want to be able to write down summations that involve lots of terms easily. Something like adding up 1 plus 2 plus 3 plus 4 and keep adding up numbers like that until you get to, 24, 25, and these large summations that would be very tedious to write out otherwise. How could we write that in a more concise notation? The notation we're going to be using is called the sigma notation. We can express this as the following summation, where we write the sum from I equals 0 to 25 of I. There are lots of parts of this summation that we'll try to identify. We call this I equals 0 the lower bound of the summation. We call the 25 at the top the upper bound of the summation. The thing inside of the summation is called the sum and what this says is starting at the value 0, plug that into the summation formula, and we get 0, because we're plugging I equals 0 into I, plus 1, plus 2, plus 3, all the way up until we get to the upper bound, and we include both the lower bound and the upper bound. You may notice I started the summation at 0, and it is exactly the same as if I had started it at 1, because that first term is 0. This can happen with summations. They can be identical to other summations, or some of the terms may actually be irrelevant because they are, in fact, 0. Let's look at a more complicated example so that we can see how the notation varies. Suppose we had the following summation. If we had the sum from I equals 5 to 22 of I squared. This says starting at 5, plug that into I squared, and we get 5 squared, plus the next value, which is 6 squared, plus the next value, which is 7 squared, plus keep going until we get to the final values, which are 21 squared, and then 22 squared. The summation always, unless somehow other specified by adding things to the notation, assumes that you start at the bottom value and increment by 1 until you get to the top value. This is going to be our main way of representing the runtime for loops, and will be used throughout a whole bunch of videos that we will see coming up in the future. It is worth mentioning, what we've done so far are strictly numerical values that you could in fact compute. We could add up the values from 5 to 22 all squared, the values from 1 to 25. We could theoretically add those up. The real power of this notation is that it allows us to represent arbitrary summations. We could write something like the sum from I equals m to n of the square root of I. This is equal to, we are start at the first value, which is m, so it's the square root of m, plus the next value, which is the square root of m plus 1, plus the next value, which is the square root of m plus 2, plus keep adding up until we get to n. So the value before n would be n minus 1, and the value for the final term would be radical n. I just used a term that you might not have identified, which is that we call the things we're adding up terms, and we actually have a formula for counting the number of things that we are adding up. With these bounds for the summation, the number of terms in the summation is n minus m plus 1. That is the top bound of the summation minus the bottom bound of the summation plus 1. This will be used a whole bunch as we go through various different summations and analyzing them. If you want to know why this is the case, the main reason is because we are including both the bottom bound and the top bound, and you need to be careful when you include those. The simple example I usually give is how many numbers are between 1 and 5 when you include them. That's 1, 2, 3, 4, and 5. And that is 5 values, so that's 5 minus 1 plus 1, 5 values. We can derive this if we want to look at a formal definition for a summation. I have one down here. Most people probably don't work with this. If you were trying to formally prove the properties of a summation, then you would need to use this definition. We will see this used a small amount, but not very much. This is mostly here if you want to see how you could mathematically deal with this without just presupposing that some basic properties hold. Now that we've introduced the notation and know what it does, our next step is going to be to try to look at some common summations and understand what are they telling us.